Hi, my name is Marina Yatsina. I'm from Intel Israel, part of the compiler team working on LLVM-based compilers. Today we're going to talk about the LLVM Greedy Register Allocator, which was introduced in 2011, and how we can improve the region split decisions that it makes. Now let's start with a motivating example. What we see here is a lot of moves, an IDIV instruction, and a lot of moves. And what actually happens is the IDIV instruction clobbers EDX. So these moves are meant to save EDX, then we clobber it, and then we restore the old value. But it's a bit strange because we have so many moves. And now the destination here is on the right. So what we see is ECX is copied to EBP, EBX to ECX, and so on and so on. All of this to store EDX, and then to restore the values back. What we could have done is chose the registers on the far edges and save EDX directly to EBP, and restore it back from EBP without changing any of the middle registers. And this code is much better than the original one and has the same meaning. So when we try to understand what caused all these redundant moves, we see that the path that inserted them was the Greedy Register Allocator. Now, in order to understand more what happened there in this example, we need to do the Greedy Register Allocator overview to understand how it works. We're going to focus on the region split mechanism because it's the source of the issue here. And we're going to talk about this issue in more details and two other issues, and the performance impact of the fixes that were committed to the open source and address these issues. So let's start with the overview. Now, this is the high-level design of the code generator, and this is where the register allocator lives. Okay, we have instruction selection, scheduling, SSA-based optimizations. This happens before register allocation, and after that we have prologue, epilogue, late machine code. And if we zoom into the register allocation, we can divide it into several phases, and we're going to focus on each one of those phases in these presentations. Now, the live interval analysis is a standalone path. And how it works is as follows. We have our CFG control flow graph, and a previous pass slot indexes added numbering to each one of the instructions. And we have an interval x, and we're trying to analyze the liveness of x. So what we do is we look at the uses and deaths of x and try to connect them into intervals. And because each instruction has a number, we actually can represent the liveness of x by a collection of segments. Now, the next phases are part of the reg-alloc greedy pass. And we're going to start with the spill weight calculation, which is this is the first thing the reg-alloc greedy does. And this is something that happens for every interval. Now, these are the intervals, the live interval analysis calculated. And now what we're going to do is look at the interval characteristics and calculate the spill weight of each interval. So things that can affect the spill weight is, for example, use density. And if W has uses in a hot loop, for example, it will have a higher spill weight. This spill weight is something that's going to be used in a later phase called eviction. Now, if X, for example, is a rematerializable instruction, it means we can cheaply copy the def, and we don't actually have to spill X, so we give it a lower spill weight. Now, the next phase we're going to do, after we calculated the weights of all the intervals, is to put them all in the priority queue. So this also happens for all the intervals. Now, these are the intervals. This is the priority queue, and now we're going to insert each interval at a time, also based on interval characteristics. Now, this priority queue determines the allocation order. It's not the same as the spill weight we just calculated. It's something different. So now we're going to determine the allocation order, and it's mostly based on if W, for example, is local to a basic block, it's going to have a lower allocation priority. If it's global and spans across a lot of instructions, like we saw X did, it will have higher allocation priority, and it will determine which one of them are we going to try to allocate first. Okay, we do this for all the intervals, and every time we're going to dequeue somebody from the queue, it's going to be the interval with the highest priority. Now, the next phases are something that happens for every interval in the queue. So here, it's something we did for all the intervals. This is also something we did for all the intervals. And now, we're dequeuing from this queue and trying to do several stages, whatever succeeds, and then dequeuing the next interval and the next, and so on. Now, let's start with the first stage, which is the register assignment. Let's say we have two physical registers in our system, R0 and R1, and this is the priority queue we have. We're dequeuing the first interval with the highest priority, which is X, and trying to assign it to an available register. After that, we dequeue the next interval and try to assign it to an available register. R1 is available, great. But when we dequeue W and try to assign it to an available register, we have a problem. X interferes with the assignment of W on R0, so we cannot just directly assign it there. And Z interferes with the assignment of W on R1, and we cannot directly assign it there. And these are all the free registers in our system currently. So what we try to do is eviction. So finally, we're going to use those spill weights we calculated in one of the early stages, and we're going to compare the spill weights of the interfering intervals, and we see that X is cheaper than W, so W is going to evict X and get assigned to R0 instead. X is going back to the priority queue, and one thing to notice is that here X is getting the same allocation priority as before. This is why it's going to get back to the beginning of the queue. And now when we try to assign X, we don't have a register that we can just smoothly assign it to, because we have interferences with W and Z. So we see if we can evict somebody. We check the spill weights. And this time, we cannot evict anybody because X is the cheapest one. So what do? We mark X as an interval to be split. We're not actually going to do the split yet. We're going to do it later on. We're just marking it to be split and putting it back in the priority queue. But this time, because it's marked to be split, it's going to go to the end of the priority queue after all the original intervals. It will receive a lower priority. We're assigning Y to an available register. And now we see that X is marked to be split, and we're actually going to try and do the split at this point. Now, first of all, when we try to do the split, we ask ourselves, is split something beneficial for us in this case? Let's assume, for the sake of example, the answer is yes. I'm going to get a bit more into that later on in the presentation in the region split section. And the second thing we determine is what is the best way to split X. For example, here, we decided to split X at these points, but is it the best way? We could have maybe split it here and here. So this is also something I'm going to talk about later on in the presentation. Now, what we do during the split, after we decide the best way to split, is actually create two new intervals and add copy instructions between them. Okay, and the original X interval no longer exists. Okay, the new intervals are the ones that are going to be take part in the allocation from this point on. Now, we take the interval, there are new intervals, so we need to calculate their spill weight. Now, please notice that this time, one of the split artifacts has a higher spill weight than the original artifact. And this can happen because maybe the split changed the characteristics, because maybe now X2 has a very high use density, but when we looked at the whole X, which already disappeared, it didn't have such high use density. So this may affect the spill weight. Now we take the intervals and put them back in the queue according to their allocation priority. And then we try to assign them. X1 assigns smoothly, there's no interferences. But when we try to assign X2, we have a problem. Y interferes with the assignment on R0, and Z interferes with the assignment on R1. So what do we do now? We try eviction, as we learned before. So we check the spill weights, and we see that this time Y is cheaper than X2. So what we are going to do is evict Y. And the thing to notice here that a split artifact evicted an original interval. Okay, and this is part of the eviction split gradual refinement process the Greedy Register Allocator is based upon. Okay, so now what can happen later on, Y can be split again and evict somebody else, and so on and so on. So X2 evicted Y, it's assigned to R0, and it goes back to the priority queue. Y is the only one in the priority queue, so we're dequeuing it. We're checking for interferences on registers. We see we cannot assign it directly to R0 or to R1. We're asking ourselves, can we evict one of them? No, we cannot, because Y is the cheapest one. The spill weight of Y is the lowest one. So what do we do now? We mark Y to be split. We put it back in the queue it again, yeah. And now we're seeing that Y is marked to be split. So we're asking ourselves, is split beneficial again? Now, let's say, for the sake of example, this time it's not beneficial. So if it's not beneficial, what we're going to try to do is spill y. Okay, so what happens is y is spilled around uses. So it's spilled after the def and reloaded before the uses. And now, again, y is spilled and creates 2 new intervals, and the old interval of y no longer exists. And what you should notice is that the middle part of y no longer exists here. We have only y until the spill. In this part, y lives on the stack, and then we have the reload. Now, these intervals are new intervals. We're going to calculate their spill weight and put them back in the queue. And now, when we assign them smoothly, and we have all intervals assigned. Everything succeeds. Great for us. Now, let's move to the region split mechanism. And if we're getting back to our motivating example, and so we already know that the path to add all these redundant moves is the Greedy Register Allocator. But what in that path made it add the moves? So if we examine a bit closely, we see that each such move duo is actually part of the artifacts of a split. So if we have the intervals, we inserted copy instructions, right? And each one of those copy instructions has translated to such move duo. Okay, this is the scenario that happened. But again, as I mentioned, we could have inserted these copy instructions in different places. We could have done the split differently. So why did we choose to do the split that way? And basically, yeah, why did we choose to do the split that way, and that way caused us trouble? So let's focus on the split mechanism to understand a bit more what happened behind the scenes in this example. So and in the overview, we asked ourselves 2 questions. How do we find the best way to split? And how do we know if split is beneficial? And this section is going to answer these 2 questions. So how do we find the best way to split? Let's assume this time we have n+1 physical registers, and x is the interval we want to split. Okay, we're in the middle of the allocation process. If we're trying to split x, we already have intervals assigned to the physical registers. These are the y and z and w we've seen before. And these intervals are the allocation constraints, and when we're splitting x, we need to work around these allocation constraints. We need to split x to not interfere with the already existing assignment. So the way the Greedy Register Allocator works, it tries, in theory, to split x for each one of the registers. I'm going to try to split x to fit the best way it can the empty spaces of R0 and cause as little spill code as possible. Then I'm going to try to split x the best way for R1, the empty spaces, and to introduce the least spill code as possible, and does that for every one of the registers. And then each such split has a cost. This cost represents the expected amount of spill code that's going to be introduced by this split. So we split x every time for a single register. We do not try to split x so it will kind of fall into place in several registers. We always try to focus on one register. Maybe this is one of the issues as well. Maybe we want to improve that. But again, and each split has a cost, and we're going to choose the split with the lowest cost, and this is the split that we're going to do. But, sorry. Now, how do we split x the best way we can for a given register? Okay? How do we split x the best way we can to fit the empty spaces of R1? So what happens is, in region split, which is the focus of our presentation, we split x mainly into 2 intervals. I call them the by register and by stack interval. Now, what do I mean by that? The by register are the parts of x that can fit the empty spaces of R1 nicely. Okay, nothing interferes with assigning x1 to R1. The by stack interval are the sections of x that have interference, because some other interval is already assigned to R1 at these places. So they cannot be assigned to R1. Now, what happens to the by stack interval is it either gets assigned to another register, R2 or R3 or someone else, or it is going to be spilled and reloaded before uses. This is why I kind of call it the by stack register. Okay, so these are the main 2 intervals that are created. And what also, again, and let's get back to the point, how do we determine that this is a good place to place copy? Why don't we place it here, or maybe a bit higher here, or maybe it's here? So in order to understand that, we need to understand what's a good split. So a good split has mainly two characteristics. It reduces the number of copies, so we want as less transitions as possible between these two intervals, and it should place the copies in colder basic blocks. We do not want to place a copy in a hot loop, because that copy will either be translated into a move between registers, or it's going to be translated into a spills and reload instructions. So these are the two main characteristics to consider. Now, what we do is we use something called the Hopfield neural network. We define the constraints and the costs, and that network converges to the solution that satisfies these two constraints. Now, the other question we asked ourselves was, how do we determine if split is beneficial? Now, split is beneficial if we compare it to a regular spill around users will cause spill code after the devs and reload before the users. And if we can split X in such a way that will reduce the number of spills, then it's beneficial. So what do I mean by that? If we look at the points where X is defined and used, at this point, X has to be in register, also at this point and at this point. And we're trying to extend the regions where X is living in a register. So if we can somehow pass X in this whole section by register, we're creating a region where X is live by register, and it reduces the number of spills. We don't have to, we don't have to reload here. Okay, so if we can find such regions, then the split is beneficial. But we cannot always find them because sorry, nervousness. We cannot always find them because the registers have already allocation constraints, and maybe the register has already Y that has to be passed between these two basic blocks by some other interval that has to be passed by registering these two basic blocks, and we cannot say both X and Y are going to be passed there by register. Okay, in this case, we cannot create such regions, and then the split is not beneficial. Now, let's talk about the encountered issues. Now, the root cause of all these encountered issues is actually a thing that is not considered during the calculation of the split cost. So I call this local interference that is caused by the split. So we may split X, and the split may cause something that's called local interference, and I'm going to explain what it is in the next slides. And we do not, and that local interference may have a negative effect. It may cause these redundant moves or a lot of spills, and we do not consider that during the split. So when we determined that the split for R1 was $10, we ignored that this may add an additional $10 and may no longer be the best split of the bunch. Okay? So what is this local interference? So when we tried to split X for R1, we were using the Hopfield neural network. Now, the network, one of the things it does, it determines how X will enter and leave the basic block, meaning how X will behave on the edges. For example, it enters basic block 1 by reg. The X1 interval, the by reg interval, is the one to enter basic block 1, and the X2 by stack interval is the one to leave basic block 1. This determines that this basic block will have a copy instruction. Okay, so basically the Hopfield neural network determines where the copies are going to be placed. But there's a problem, because the Hopfield neural network does not really consider what happens in the middle of the block. It only looks at the entrance and the exit of the block. Okay, and the middle of the block may have a problem. So let's focus on that middle. And local interference actually happens when X1 is determined to get into the block by register and get out of the block by register, and we have a local interference. We have some interval Y already assigned to that register in the basic block, and it's, again, local to the basic block. This is why it's local interference. And we have also uses in X of X in that basic block. So what happens here is that we have this local interference, and in this part, because of the interference, X cannot be passed in the x by reg interval, it has to be passed on the by stack interval. And when we have such a local interference, this causes us a lot of trouble. So we're going to see 3 cases. The first 2 cases are something I call bad eviction chains. And the third case is a case of a lot of reloads. And all of this was caused because we did not consider that this interval here might cause us a lot of trouble. Now, these 3 cases, I have committed solutions that are tailored for these very specific scenarios, and probably there are scenarios that involve local interferences that I missed. And what I think is looking back, I think the end solution should be a holistic solution to understand what is local interference, what are the effects that it can do, how many spill code it may introduce, and take that into account in the split cost. So let's start with the first scenario, which was our motivating example. So let's understand a bit more now that we know how the split and eviction chain work, what happened here. So if we look at a move duo again, we see that what happens is that Y evicts X from EDI. So I call this cyclic eviction split chain. So we're starting to see the first part of the circle. Y evicts X. Y is placed into EDI. X is split into 2 intervals. One of the intervals, X1 this time, is the one that has the local interference with Y. Okay, and now what happens is that X1 evicts Y back again. Okay, so here we get the circle. Y evicts X. X is split, and the interfering part of X evicts Y again from the same register. Okay, so each such duo mapped to a different eviction circle. Okay, so if we summarize, the problem was that the X was split in such a way that created this local interference, and that local interference caused us a lot of trouble. In this case, this eviction circle. The solution, as I mentioned, was tailored to this specific case. I was looking for splits that create local interferences, and those local interferences cause and try to predict if those local interferences cause this cycle. And for this split, I increased the cost to make it less favorable compared to other splits. The commit, this is a link to the commit. And now we're going to move to the second example, which looks quite similar. We also have these chains of XMMs, of moves between XMMs, and then we're kind of restoring them. This time, part of the chain is spread around. There's more code here that I didn't put in the slide. Now, what happens if we also start to look at an eviction duo? It's something I call domino effect eviction. It's a bit different from what we've seen with the cyclic eviction. So this time, X evicts Y from XMM2. Then Y is split to fit XMM2 best, and we have the local interference with X. And that local interference part of Y, it cannot evict X from XMM2. If it could have, we would have had the cyclic eviction again. But this time, what it does, it evicts somebody else from XMM3. It evicts Z. So we can see here the start of the domino effect. X evicts Y. Y is split. The part of Y evicts Z. And then Z is split. The interfering part of Z cannot evict Y, but it evicts somebody else. And then it is assigned to XMM4, and so on. So we're trying to see this domino effect. We're starting to see this domino effect here. And every such additional move is part of the domino effect. Okay, so the problem was that Y was split to fit the register it was just evicted from, so it also has high chances to cause local interference, and it indeed causes local interference, and that local interference causes this domino effect chain. The solution was to catch this specific case, where we split Y for the register it was evicted from, and increase the split cost of that case to make the split less favorable than others. And this is a link to the review. Both of the bad eviction scenarios were fixed in the same review. Now, the third scenario is a bit different. I call it the multiple reloads. So as we see, you have here multiple reloads from the same location. And what's weird about it is that it appeared in a hot loop after some higher level change, which was a good change. It was a good optimization. So what happened, if we look at the machine function, the loop basic block is exactly the same just up until the Greedy Register Allocator. And the Greedy Register Allocator was the one to introduce this reload code. So we tried to understand what happened there. So of course, there was a higher level change. Other basic blocks have changed a bit. Other intervals have changed a bit. So the allocation will change in this basic block again. But why was it so bad? So if we just compare what happened, we see that before the change, X was split for some register R0. After the change, it was split for another register R1. But what's interesting is that when it was split for R0, it did not have any local interferences. But when it was split for R1, it had local interferences in the loop, in the machine basic block of the loop. And what also was there is that X had a lot of uses in that loop, and it ended up spilling. It couldn't find good allocation to another register, and we have all those reloads before every one of those uses. So if we conclude, the problem was that the local interference had a lot of uses in the hot loop, and the interval was spilled and reloaded a lot. So again, solution was really tailored for this case, and we increased the split cost for this case. And this is the review for the commit. And the performance impact of the results. So the first two changes that were done in a single commit, these are the workloads that were affected by the change, like above or below 2%. These are mostly embassy workloads, bench, automotive, and the regressions were not related to this change. The allocation changed, the layout of the basic blocks changed, so it was not. It was still good decisions. We caught good scenarios of chains. And the compile time effect on CityMark, which is the compile time benchmark of LLVM, there was no real change in the compile time. And issue number 3 also has nice results. And it's also mostly embassy workloads and no actual compile time effect. So if we conclude, local interference caused by split may have a negative effect, and the current split cost does not model that effect at all. So the committed solutions address 3 very tailored scenarios and very specific scenarios. There are probably a lot more, and we do need a holistic approach, maybe involve some study with academia. How can we model this correctly and take it into account during the split? Thank you.
Thank you, Marina. So now we have about 7 minutes for questions.
Regarding that neural network stuff, so what did you train and what did you use there?
It's not it models a given neural network, and it kind of let's say this whole hopeful neural network could be a whole section of its own, but it's a given network that converges it's converging to a local minimum, and when we model that network correctly, that local minimum represents the minimum spill code and its placement. So it's a given network. I think it's used in physics or something mostly.
Any other questions? No more questions? Okay, thank you. Let's thank Marina again.
Thank you.
Thank you very much.